Okay, so hello everyone. My name is Lohit Kwan, and indeed this is the 11th live session of the Introduction to Interfacial Waves. Okay, so today we will mostly talk about Faraday instability. So let me share my screen, then we will start discussing. Okay, so before discussing about the Faraday wave, so we will do a small exercise about the shape of the oscillation of a bubble. So remember what was the formula? That omega square equal to some n into n minus 1 n plus 1 plus 2 t by r naught cube. Just let me check the formula once. Here r naught is the radius of the bubble or the sphere. Now the question is for n equal to 0 and n equal to 1, omega square equal to 0, that means there is no oscillation. That is fine. Now what is the physical significance of n equal to 0 or n equal to 1? We now need to understand. Okay. Now to do that, let us do this exercise. So, what is the volume of the part of bubble? We need to determine that. Now, what is the volume of a sphere? How to determine the volume of a sphere? Suppose this VSP is the volume of sphere. Okay, that is 0 to 2 pi. Remember the. Let me draw the sphere first. It might be R. One angle. This angle is phi. Phi is varying from 2 pi to 0, and this with the angle with the z axis, this is theta. Theta is varying from pi to 0. Now, if you consider a small volume element, its volume is dV, and if you integrate it over the entire domain, you will get the volume of your sphere. And the formula is r square sine theta, then d theta d phi d r. Now, integration of d phi is the easiest because there is no component of d phi is present. So, we will just take 2 pi. 2 pi we will take outside. Then it will be 0 to pi, then 0 to r naught, r square sine theta d theta d r. Okay. Now, integrate with respect to r and we will get 2 pi. So, integration of r square will be 2 pi by 3, 0 to pi r naught cube sine theta d theta. It is correct. So r naught is again a constant. It will be 2 pi r naught cube by 3, 0 to pi sine theta d theta. Now integration of sine theta is minus of cosine theta. So it will be minus of 2 pi r naught cube 3 into cosine theta 0 to pi. So if you calculate, you will get 4 pi r naught cube divided by 3. So this is your area of the sphere. Okay. Now you have provided some perturbation. Okay. So in the formula, what will change? We will have to now include r naught plus eta. Okay. So instead of r naught cube, we will have r naught plus eta whole cube. Okay. So let us do that. So now VSP will be 2 pi t. Remember that we have considered that it is axisymmetric, so eta is not function of a phi. Okay, eta is function of theta and t only. Okay, 0 to pi r naught plus eta whole cube of sine theta d theta. Alright, okay. So now we will expand this quantity. So we will have 2 pi by 3, 0 to pi r naught cube plus 3 r naught square eta plus order eta square. We will not consider the nonlinear terms of eta. Okay, we will consider only the linear terms theta d theta, and it will be equal to 2 pi by 3, 0 to pi r naught cube plus 3 r naught square eta sine theta d theta. So we can divide it in two parts. So 2 pi r naught cube by 3 integration 0 to pi sine theta d theta plus, so 3 r naught square is again the constant, it will be 2 pi r naught square integration 0 to pi eta sine theta d theta. Now we have already calculated, it will be 4 pi r naught cube by 3, that is the volume of the unpart of sphere. Okay, plus 2 pi r naught square 0 to pi eta sine theta of d theta. Okay, there and VUN. This is the unpart of sphere, volume of the unpart of sphere, right? Now remember that each form of eta was something like is some constant a into e to the power of I omega t into PL of cos theta, right? This was the form of your eta. So we will substitute this form. Huh? So it will be VUN plus 2 pi r naught square. Remember, a is constant, e to the power I omega t is not also a function of theta. So we can pull those out. Into a into e to the power I omega t 0 to pi PL cos theta sine theta d theta. Okay. Now let us substitute x equal to cos theta. So we'll get dx equal to minus sine theta d theta. So we will get DSP equal to VUN. Remember, VUN is the volume of the unpart of sphere. Plus 2 pi r naught square into a into e to the power of I omega t from minus 1 to 1 PL of x dx. Okay, this is the formula. So if you just substitute it, you will get it. Now there is an identity in the Legendre for the Legendre function, and that is this is the orthogonality relation. Which is minus 1 to 1 PLX PNX dx equal to 2 by 2n plus 1 delta Ln. Well, that means equal to 2 by 2n plus 1 when L equal to n and equal to 0 when L not equal to n. Okay. Now, and we have this function minus 1 to 1 plx dx, and minus 1 to 1 plx dx, I can write it like this: minus 1 to 1 plx p0 of x dx, because p0 of x is equal to 1. Now remember, what is PL of x? PL of x is the initial shape of your perturbation. Okay. If L equal to 1 or 2 or 3, then this value will be 0 from this orthogonality relation. That means your volume of the part of sphere will be volume of the unpart of sphere. So there will be no change in volume, right? But if L equal to 0, then this is not 0. Okay. Then this term will be equal to 1 to 1 PL of x P0 of x dx equal to 2 by 2 into 0 plus 1 is equal to 2. So your volume of the part of sphere will be volume of unpart of sphere plus 2 pi r naught square into a into e to the power I omega t into 2. So it will be a function of time. Okay, that means so what will happen physically? See that for L equal to 0 there is no oscillation. Okay, now if you're so suppose your initial shape of the sphere is like this. Okay, but after some time the volume of the shape of the sphere will be something like this, because it will change the volume. So I have drawn it badly because the center will be the same. Okay, again at some time the shape will be something like this. That means it will just change the shape. It will shrink down, or it will or the shape of the bubble will increase. Okay, but there will be no oscillation. Okay, so this is the physical significance of L equal to 0. So the shape will not change. It will either collapse or the size of the bubble will increase without any oscillation. Okay, all right. And you can actually calculate the volume also. Okay, let me just do that for you. Sorry, they calculate the radius also, the approximate radius. So, what is your VSP? VSP is 4 by 3 pi RT cube. Well, what is RT? RT is the instantaneous radius at any time. Okay, RT. Oh, sorry, I have. What? Suppose this is your RT. It is the instantaneous radius, because the because the shape radius of the bubble will always change. Okay, 4 by 3 RT cube equal to 4 by 3 pi r naught cube, where r naught is the initial radius of the bubble, plus this exponential term, that is 4 pi r naught square into a into e to the power of I omega t. Sorry, this is not the initial radius, this is the radius of the base state. Okay, this is not the initial radius. Sorry. Now at t equal to 0, 4 pi by 3, I am assuming at t equal to 0, RT is equal to R. 4 pi by 3 R small r cube equal to 4 pi by 3 R naught cube plus 4 pi R naught square into A. So I can take 4 pi by 3 as common, and I will get R naught cube plus 3 R naught square into A. Huh? Now, if we add the term like 3 R naught A square plus A cube, then it will be 4 pi by 3 R naught plus A whole cube. But we don't have those terms. Why? Because we have considering that this is a linear thing, linear pattern, linear solution. Okay, so A square and A naught A cube are those are very small terms, so we can neglect it. So we can approximately write it like this. So 4 pi by 3 small r cube equal to 4 pi by 3 r naught plus A whole cube. So your r instantaneous radius at initial at r equal to 0, it will be r naught plus e. Okay, so this is zero oscillation, but the size of the bubble or the size of the sphere will change. Okay, so this is the physical significance of your L equal to 0. Huh? Now, what will happen for L equal to 1? We need to find out the physical significance for L equal to 1. Why omega is 0 here? Okay, so let's do that. Okay, so if we want to track the center of mass for the sphere, huh? So let us calculate what is the formula Z Cm. Say Cm is the center of mass, the vertical position, that is r cos theta dv divided by integration of dv. So if we for a sphere, for a sphere, what will we get? We will get 0 to 2 pi, 0 to pi, 0 to r naught, r cos theta, and what is dv? dv is r square sine theta d theta dr d phi. And we already know what is the integration of the volume, that is 4 by 3 pi r naught cube. I have already got it. Here I will get, let us do the calculation first. So 2 pi will come out, okay. Then r cube will be r to the power 4, r naught to the power 4 by 4 by 4. Then integration 0 to pi cos theta sine theta d theta divided by 4 by 3 pi r naught cube. So pi will get cancelled. So it will be 6 by 16, that is 3 by 8 into 3, and this cancel into r naught, right? So for the sine theta cos theta, I will take it to 1 by 2 outside. It will be 0 to pi sine 2 theta d theta. Okay, so it will be cos 2 theta, and if we can do the calculation, we'll get this is 0. So for the unpart of sphere, the center of mass is at the origin of the sphere. Okay, now what will happen if we just part up it? Huh? So let us now do the calculation. Okay, so is r naught plus eta, and it will be 4 by 3 r naught cube plus that constant 4 pi r naught square into a e to the power omega t into a, okay, plus into a, okay. No, so now this will change, okay. So we'll have 2 pi by 4 into half into 0 to pi r naught plus eta whole to the power 4 sine 2 theta d theta. Okay, so we'll now do this calculation. Again, we will use the linearized approximation. Let us first remove this calculation. Now, for the linearized approximation, we will get pi by 4 into, so it will be r naught to the power 4 plus 4 r naught to the power cube into eta 0 to pi r naught to the power 4 plus 4 r naught cube into eta into sine 2 theta d theta. Okay, divided by 4 by 3 pi r naught cube plus those term multiplied with a. Alright. So this first quantity you have already got that will be 0. Okay, so we will not bother about that. So because sine 2 theta d theta integration 0 to pi will be 0. So now we will get pi r naught q 0 to pi eta. Now let's expand this sine theta to theta. It will be 2 sine theta cos theta d theta divided by that term. Now let us only focus on this integration. Eta sine theta cos theta d theta. Okay. Let us again assume that x equal to cos theta. So it will be minus 1 to 1. Okay, so eta we know that some a into PL of cos theta. You have already know that. That will be PL of x into dx. Okay. Now we will again use the orthogonality relation because x is equal to p1 of x. So it will be minus 1 to 1 plx p1x dx because your p1x is equal to x. So the result will be 2 by 2 plus 1 into delta 1L, 2L plus 1 into delta 1L. Okay. That means if L equal to 2, 3, 4 or anything, huh, then your this value will be 0. That means your ZCM, that means the numerator will be entirely 0, denominator is non-zero, so your ZCM will be 0. So the center of mass will stay at the origin. Now, if your L equal to 1, then your numerator is non-zero, denominator is already non-zero. So you will have a non-zero ZCM, right? So it suggests denominator there is a time dependent, there is a e to the power I omega theta, right? So it suggests that your center of mass, suppose this is a sphere, at some time it will go to this location, okay, because it can move up or sometimes it can move down. It will move down, okay, where without any oscillation. So this is a sphere, so it is sometime it will move up, it will sometime move down because your ZCM is non-zero. Okay, so this is the physical significance of L equal to 1. So for L equal to 0 and L equal to 1, you will have you will not have any frequency. Okay, for L equal to 0, your volume can increase or decrease, but when the problem is when the fluid is incompressible, so then L equal to 0 is not allowed at all. Okay, but for L equal to 1, your center of mass will change, so your bubble some will move forward or move up or down. Okay, so these are the physical significance for L equal to 1 or and L equal to 0. Now we will move to Faraday state. Just give me a moment. So what a Faraday instability? So we have already done the problem related to couplings of pendulum. We get a Matthew equation from there. So here the idea is to derive the Matthew equation from a practical problem. And the problem is, in the class it was derived for the your gravity driven case. So the problem statement is, you have some container lighting, there is some fluid, and you are oscillating it, okay, with the forcing of like of this kind F cos omega t. That means your this container is oscillated. As a result, your interface is also going up and down. Okay, so this is your physical condition. This is called Faraday instability. Now, suppose you have provided a perturbation to your initial condition, then what equation will govern the evolution of the interface? That is the main question. Okay, so I will solve for two different cases. One will be in the Cartesian geometry, another will be in the cylindrical coordinate. And I will leave it to you to solve it for the spherical coordinate, because in the last class we have done so many derivation about the spherical coordinate. Okay, so now for the Cartesian coordinate, this is our problem statement. Huh? So suppose this domain is varying from minus L to L. So there is a boundary. We will assume that it is infinitely deep. This is minus infinity at the z direction. For the simplicity of our calculation, we have already discussed that, right? And we are providing it perturbation, and this is the forcing. Okay, so let us first solve it for the Cartesian geometry. So what is the governing equation? Governing equation will be phi equal to 0, because this is the implicit. Huh? Then the other equation is del phi del x at x equal to plus minus of L equal to 0. This is the no penetration condition at the boundary. Huh? Then phi at z tends to minus infinity equal to 0. This is the finiteness condition. Huh? Then to the two important boundary condition, that is del eta del t is equal to del phi del z at z equal to 0, and del phi del t plus g plus f cos omega t, hmm, into eta minus p by rho del square eta del x square equal to 0. We have derived this equation except this term. So here you can treat that your gravity is changing. Gravity is a time dependent function, because the oscillation that we are providing on the container, it is actually body force, right? It is modifying your gravity. So this is my entire equation, and now we have to solve this. All right. So we for unforced case, we have already know the solution. We know the what will be the solution in the spatial domain. So let us just do that, and we'll so it can't be solved using the normal mode analysis because of the presence of this term. So we will treat it as an initial value problem. Okay. So let me take that phi x z t is equal to uh, p of t cos kx into e to the power of kz. Now question is, what is k? K is coming from this equation. K is sine kl is equal to 0. So k is here actually in pi over l. So kn. Okay. So let me just write kn. Knz. So it will be more appropriate. Hmm? Or you can write it like this: bt equal to cos n pi x by l into e to the power n pi z by n. Because your kn is equal to n pi by n. Okay, so let us write like this. So n can be 1, 2, 3, anything. And your eta xt will be at cos n pi x by n. Now if we put it in this two equation, we will get a dot is equal to n pi by L to B. And from the second equation, so we will get B equal to A dot by n pi by L. Okay. And from the second equation, we will get del phi del T, that is B dot plus G plus F cos omega T, G plus F cos omega T multiplied with eta. Eta is your A plus T by rho del square eta del x square. So I will simply get n pi by L whole square T by rho into A is equal to 0. Now your B dot will be B, I can substitute it from here. So I will get A double dot plus G plus F cos omega T n pi by L plus T by rho n pi by L whole cube into A is equal to 0. So this is your differential equation for A. Now remember that when your f is 0, then we can solve it using normal mode analysis. Okay. Now here we have to solve it numerically. So that is not a concern. Now we have to convert it to the well-known Matthew equation. So for that I will do this. So A double dot plus G into n pi by L plus T by rho n pi by L whole cube. Is this form familiar to you? This is just gk plus tk cube by rho. Okay, that is the original frequency of the system. Plus f cos omega t into n pi by L times A is equal to 0. Okay. So let us define omega 0 squared is equal to g into n pi by L plus t by rho n pi by L whole cube. Huh? And we will define the transformation omega t is equal to 2 capital T. Okay. So my d square A dt square, it will be omega square by 4 d square A dt square. Okay. We'll get d square A dt square plus 4 divided by omega square. This will be omega 0 square plus f cos, sorry, into n pi by L times cos 2 into A is equal to 0. So I will take 4 by omega square inside and I will get d square A dt square plus 4 omega 0 square by omega square plus 4 f n pi by L divided by omega square cos 2t into A is equal to 0. So we can consider this one constants. This is in non-dimensional quantity. If you calculate, you will find this is also non-dimensional quantity q. So d square A dt square plus p plus q cos 2t times A is equal to 0. Okay, but p is your non-dimensional frequency. Q is your non-dimensional forcing. Okay. Now, if your P equal to 1, okay, that means your 4 omega 0 square by omega square is equal to 1. That means your omega 0 is equal to omega by 2. That means your response frequency. Omega 0 is the response frequency of your interface, right? It is the half of the forcing frequency. This case is called the subharmonic case. So I will show shortly that for this case it will be an unstable situation. That means the wave will grow. Now when P equal to 4, your omega 0 is equal to omega. That means your response frequency is same as your forcing frequency. Okay, this is called the harmonic case. All right. So this is the harmonic case. Now, so now for this case also, the system will be unstable. Okay, I will not show it, but you can derive that. Okay. So this is the case that is Cartesian geometry, right? Now let us do it for the cylindrical geometry. Okay. For the cylindrical geometry, we will have equal to 0. Okay, and del phi del r equal to r naught equal to 0. This is the no penetration condition. This is the kinematic boundary condition. This is the Bernoulli equation at the interface. Okay. So we know the solution. The solution will be eta rt equal to at j0 ln by r naught times r. Now what is ln? It is coming from this expression, right? We'll get, so we will get j1 ln is equal to 0. So ln is basically the roots of j1. Huh? So it is eta rt and phi rzt will be similar to this. It will be this will be at. This is bt j0 ln by r naught into r e to the power ln by r naught into z. Okay. All right. So now the rest of the calculation is just same as the Cartesian coordinate. Okay. But the final result, if you substitute it, you will just get t by rho ln by r naught whole square into 80. In the last case, you are getting n pi by l whole square. Okay. Here you will get ln by r naught whole square. Okay. So if you do the inter substitution, you will find that you are again getting this expression that d square a d t square plus e plus q cos 2t a equal to 0 but p equal to 4 omega 0 square by omega square and q is equal to 4 f l cube by omega square. Okay, just similar to the Cartesian geometry. So you can do this exercise for spherical geometry as well. For the sphere, you can also imagine the forcing has to be in the radial direction. Okay, the forcing has to be in the radial direction, in this direction. Okay, the forcing. All right. Now let us try to solve this equation analytically. Okay? So we already know about the technique that is called the multiple scale method. Okay? So we will utilize the multiple scale technique to solve this problem. Okay. So now solve it for the subharmonic case, that is omega 0 is equal to omega by 2. That means your p will be equal to 1. Huh? Now we will not exactly solve for 1. We will give it a small perturbation, and the small perturbation is we will consider p equal to 1 plus epsilon delta 1. That is a small shift from the subharmonic frequency. Epsilon is a very small quantity. And we will also approximate forcing term, that is small, and we will assume that q equal to epsilon. So we are considering only small forcing. This epsilon is not very for the forcing is not very important. We just want to show that for near the subharmonic point, subharmonic regime, what will happen if we apply only a very small amount of force. We want to find that out. Okay. All right. So what is our equation? Our equation was d square a dt square plus 1 plus epsilon delta 1 plus epsilon cos 2t times a equal to 0. Okay. Now let us assume that tau equal to epsilon t. So your d dt will be del t plus epsilon del tau, and d square dt square is equal to, in the linear regime it will be del. We have already done it in the past. Okay, so I will just write the final expression, and you already know about all this. T del capital T del tau. Okay. Now we will expand our a like this. A equal to a0 plus epsilon a1. Okay. So at order 0, we will get del square a0 del t square plus a0 is equal to 0. So what is the solution? A0 equal to a tau e to the power it plus cc. Now at the linear order, at order epsilon, huh, what will be the solution of this? Solution will be del square a1 del t0 square. Uh, okay, so let us first do it like this. So I will put this term. So I will get del square del t square plus 2 epsilon del square del t del tau a0 plus epsilon a1 plus 1 plus epsilon delta 1 plus epsilon into cos 2t, that is 2 into a0 plus epsilon a1. This is the entire expansion. So I will let me expand it and write the terms. This implies del square A naught del T square plus epsilon del square A1 del T square plus 2 epsilon del square A naught del T del tau plus 2 epsilon square del square A1 del T del tau. Okay. Now on the second term, I will get A naught plus epsilon A1 plus epsilon delta 1 A naught plus epsilon square delta 1 A1 plus epsilon A naught cos 2t plus epsilon square A1 cos 2t. Now we will consider only terms up to order epsilon. Okay? So we will neglect this term, and this term. So for order epsilon, pardon me, for order 1, we have del square A naught del t square plus A naught is equal to 0. Okay, and the solution of this will be A naught equal to some E tau e to the power I t plus its complex conjugate. Okay, now for the order epsilon, del square A1 del t square. So for order epsilon, we will need to take this term, this term, this term, this term, and this term. So let me just write that down. So A1 del t square plus 2 del square A naught del t del tau plus A1 plus delta 1 A naught plus A naught cos 2 tau cos 2 t equal to 0. This implies del square A1 del t square plus A1 equal to minus 1 plus delta, sorry, minus delta 1 uh, delta 1 A0 minus cos 2t into A0 minus 2 del square A0 del t del tau. It will be equal to minus delta 1 A e to the power I tau minus e to the power it plus e to the power minus it divided by 2. Huh? So I will now write the CC term as well. For only for this term, you will understand why. So it will be A into e to the power I t. Sorry, it will be 2it minus 2it plus A star e to the power minus it. Okay, 2 del square A naught del t del tau 2 del A del tau into e to the power it. Right? There will be some other complex conjugate terms. Now see that this is the equation. Okay. Now for a differential equation like this, suppose you have equation square x dt square plus x is equal to cos t. Now, if you are told to find the fundamental solution, so what will be the case? What will be the answer? So then you need to solve it case for the particular integral and the complementary function. The complementary function will be something like this: a cos t plus b sin t. And for the particular integral, you need to take xpi equal to c1 t cos t plus c2 t sin t. Now let us substitute this here. This is the particular integral that is coming from the non-homogeneous part. If we substitute, so now dx dt, it will be c1 cos t minus c1 t sin t plus c2 cos t plus, sorry, c2 sin t plus c2 t cos t. So d2x dt square will be minus c1 sin t minus c1 sin t minus c1 t cos t plus c2 cos t plus c2 cos t minus c2 t sin t. So you will have minus 2c1 sin t plus 2c2 cos t minus c1 t cos t minus c2t sin t. So d square x dt square plus x will be equal to minus 2c1 sin t plus 2c2 cos t minus c1 t sin cos t minus c2t sin t plus, this is coming from x, c1t cos t plus c2t sin t is equal to cos. So these four terms will get cancelled, and from comparing the left hand side and right hand side, we will get c1 equal to 0 and c2 equal to half. Okay, so your x I is equal to half t sin t. So your total solution is equal to a cos t plus b sin t plus half t sin t. Okay, so this will be integral solution. Now, if if on the right side there is no cos theta, huh, then this term will not appear. T into sin theta will not appear. Okay, so then it will be just an oscillatory term, oscillatory solution. But as the presence of this term on the right hand side, cosine, I am getting term like half of t sin t. Okay, so when t tends to infinity, x is tends to infinity. Because of this t term, it will increase linearly. Okay, so the solution will diverge. That is the main problem. So that is the main problem. Now on the right hand, anything other than cos t, anything other than cos t or sin t. It may be cos 2t, sin 2t, cos 3t, sin 3t, anything. Suppose we let us consider case of cos 3t. If you have this on the right hand side, huh, then you can choose your xp, that is a particular integral solution, equal to c1 cos 3t plus c2 sin 3t. Huh? So if you substitute it, solution will be some constant into cosine of 3t. So when x tends to t tends to infinity, it will be anyway an oscillatory solution. Okay, so the problem appears because the solution, the complement solution of the complementary function of this equation, that is also the form of cos t and sin t, and the solution and the non-homogeneous term, they are equal. I mean, they are similar. This is in physics. This is called resonance. Okay, because this is like the forcing. This is just like the forcing. And if your original frequency is same as this thing, then the solution will grow exponential. The solution will grow in time. Okay, so now, so that is the unphysical situation. Because the solution, we don't need a solution like that. Now here also you see that here the solution of the homogeneous term is of the form of e to the power I t. Huh? Now on the right, as e to the power I t means cos t or sin t. Okay. Now on the right hand side, if you have terms like e to the power I t, then there is a problem. So we need to remove that term. Okay. So that is our whole idea. Okay. E to the power I t. Okay. That. So we will have del square a1 del t square plus a1 is equal to see. Now see that this term is not problematic, but those term which is containing e to the power it, that is problematic. So we have to remove that term because that is an unphysical situation. Is arriving from the situation. It is arriving in the problem because we are expecting an oscillatory solution. Okay. So we will have equal to minus, yeah, minus will be outside, delta 1a plus 2 delta a delta tau plus a star by 2 e to the power it plus some term will be there. So this term has to be equal to 0. Oh, sorry, there will be I. And I will be outside. Sorry, sorry. I am making. So we need to have 2i del a del tau plus delta 1 a plus a star by 2 has to be equal to 0. Now, how to solve this? Here a is a complex number, complex variable. So we will assume a equal to u plus iv, where u and u star, u and v are real. Okay. Yes, so let us write it down completely. So I will get del u del t del tau plus I del v del tau plus delta 1 u plus iv plus a star by 2 plus half u minus I v. Now we need to separate the real quantity and the imaginary part. Okay, so we will have minus 2 del v del tau plus delta 1 u plus half u is equal to 0. This is from the real part, and from the imaginary part it will be 2 del u del tau plus delta 1 v minus half v equal to 0. This is from the imaginary point. Okay. So we have two coupled ordinary differential equation. Now we need to solve this. So there are many ways that you can solve it. I will probably show the easiest one. Just differentiate it with respect to tau once again. So we will get sorry minus 2 del square v del tau square plus delta 1 plus half del u del tau is equal to 0. And I will substitute del u del tau from this equation. And what is the value of the del u del tau? Del u del tau is equal to, according to this equation, it will be 1 by 2, it will be on the outside, 1 by 2 minus delta 1 into v. If I substitute it here, I will get minus 2 del square v del tau square plus delta 1 plus half into half minus delta 1 into v equal to 0. So if I divide it by minus 2, I will get okay. Just a second. So now this is an ordinary differential equation and we can solve this. Okay. But we are not interested in entirely solving it. We just want to find some stability criteria. Okay? Or we can just, just let us just solve it. So this is some, let us give it a name alpha square, where alpha square equal to 1 by 4 delta 1 square minus 1 by 4. So what will be the solution? So v tau will be some e to the power of I alpha tau plus cc. Okay. Now what will be the u tau? U tau, obviously that will be the question that we can get easily from this equation. Okay. So what the standard equation says, it is minus 2 del v del tau plus half plus delta 1 u equal to 0. So we'll get minus 2 I alpha e to the power I alpha tau plus delta 1 u equal to 0. So u equal to 2 I alpha e to the power I alpha t tau divided by half plus delta 1 plus cc. So in general, what will be your solution? Your solution is u plus iv, right? A, that is your A. So that will be 2 I alpha by half plus delta 1 plus I into v alpha tau into e to the power I alpha tau plus cc. And it will be multiplied with, and what will be your, just a moment, what was unknown term? A small a of t, right? So small a of t will be a tau into e to the power I t. So finally I will get e to the power I 1 plus alpha. Okay, now e to the power I t plus I alpha tau into multiplied by something plus cc. Okay. Now what is tau? Tau equal to epsilon into t. So we will get e to the power I t plus I alpha epsilon t. So we will get e to the power I t plus epsilon 1 plus epsilon alpha into t. Now see, here is an interesting thing. Uh, Here, this is a real number. Epsilon is small and a real number. But what about alpha? Can we say that this is a real number? What is the expression of alpha square? Alpha square equal to 1 by 4 into delta 1 square minus 1 by 4. Now alpha square is greater than 0 when delta 1 square minus 1 by 4 is greater than 0. That means this is a real number. For real number, I don't have any issue. It will be an oscillatory solution. That is our desired result. Because why? Because okay, epsilon. What is the original? What is the original equation? Yeah, this is this one. Then epsilon is a very small number. If there is only 1 plus epsilon delta 1, we will only have oscillatory solution and we have part of it by a small amount. So obviously we are expecting an oscillatory solution with some kind of modification. So if the solution is not oscillatory, then there is some problem. Okay. Now the problem appears when alpha square is less than 0. That means e to the power I alpha, this alpha will be an imaginary term. So there will be a growing term in this expression. Okay, alpha can be treated as alpha r plus I alpha I, and if I multiply it with I, then I alpha r will be an oscillatory part, but minus alpha I will be an growing part. Because it will be plus minus of alpha I, so it will be plus minus of alpha e to the power plus alpha it will be a growing solution. That is undesirable. Okay, so that is not entirely undesirable for one thing. So now I will discuss about that case. So this is a very interesting case. Now, when alpha square is less than 0, we see that there will be a growing solution, that is an unstable solution. Okay, that means the solution will look something like this. It will exponentially grow in time, e to the power plus alpha it because of that. But it will slowly grow in time because it is one epsilon will be multiplied with it, but it will eventually grow in time. So for the alpha square is less than 0, that means your delta 1 square minus 1 by 4 is less than 0. That means your delta 1 is less than half, less than of minus half. Now remember, what is this delta 1? The 1 plus epsilon delta 1. So if I multiply with epsilon, so epsilon delta 1 is less than epsilon by 2 minus epsilon by 2. Now we have already discussed that p equal to 1, that is the subharmonic case. Okay. Now, for a very small neighborhood near p equal to 1, for a very small neighborhood, your solution is unstable, whatever be the forcing is, because epsilon is a very small forcing term. When epsilon tends to 0, for 0, even for a very, very, very small forcing, at p equal to 1, your solution is unstable. That is, it will grow in time. But when away from this neighborhood, suppose this is a p equal to 1 and this is this very small neighborhood, but away from this neighborhood, your solution is stable. Okay, this is your stable region away from that neighborhood. That is a very interesting result. From for a very small region, your solution is unstable, it will grow in time, but for a distant region, it will be stable. Now I will give you one task to do, that you solve this problem. You solve this problem, but solve it for p equal to 4. P equal to 4. Make it 4. Do it for 4 plus epsilon delta 1 and try to solve it. There also you will find a region, you will find a neighborhood where the solution is unstable, and apart from that the solution is stable. Again you will find the same thing 16, 25. Okay, this thing will repeat. Okay, so as a result, you will get a stability chart of your P and Q. P, sorry, this is Q, this is P. Suppose this is P equal to 1, this is one stability chart. Inside this region, because we have talked about this neighborhood, there is a neighborhood. Okay. Within that neighborhood, whatever be your forcing is, the solution is unstable. Q is the non-dimensional forcing, right? At P equal to 1. Similarly, at P equal to 4, you will again find similar region. At P equal to 9, you will get similar region. 16, similar region. So in this region, it is stable, stable, stable. Inside this region, it is unstable, 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 unstable. Because this is one very interesting result from the Matthew equation. Okay. Now you can also solve it numerically. If you solve it numerically, then you will see that these are so this multiple scale method is applied only when your forcing term is one. Okay. If you do it for, if you knew there is a way to solve it numerically, if you do that, you will see that that your term look actually like this. It will bend. Okay, this something like that. This will bend over if you do it for a larger forcing, but you cannot do that analytically. You need to use a computer to solve that. Okay, but that is not required. But I think the idea is clear. Why around 1, 4, 9, 16 the solution is unstable. Okay. All right. So I wanted to show today. So now let us solve some assignment problem, and we will finish for today. Okay. So in case of Faraday waves at the base state, the pressure field is oscillatory in Z, oscillatory in T, oscillatory in X, and or linear in Z. So that is one interesting question because we have I haven't discussed this. So consider your Euler equation. Huh? So del U del T plus U dot grad U is vector, vector is equal to minus grad P by rho plus GT Ez, right? This is the term. Now at the base state, your U hat is 0. Only P will be there. So grad P is equal to G of T. This is oscillatory in time. So your pressure will be oscillatory in time. So answer B is the correct answer. Okay. Otherwise, P will be just minus rho GZ. Okay, we all know that. Now inside the first subharmonic term, that means for P equal to 1, the oscillation frequency of the system is, now what is, now you need to go to the definition of P. P equal to 1 equal to 4 omega 0 square by omega square. So omega 0 is equal to omega by 2. So the oscillation frequency of the system is half of the driving oscillation frequency. So this is correct. So if I ask you the question that what will happen for the third subharmonic term, okay? For third subharmonic term, P will not be equal to 3. Okay, because for the third subharmonic term, your omega 0 will be 3 omega by 2. And your P will be equal to 9. Okay, so this will be the case. Now, select the correct statement. Oscillation of an unforced linear simple pendulum is analog to the linear Faraday instability problem. No, the unforced pendulum is similar just normal surface gravity of some surface normal surface waves problem, right? We have seen that for the normal surface problem we get the term cos t, but the simple pendulum we also get the term cos t, the simple harmonic oscillation. Now second question is, the oscillation of an unforced simple pendulum is linear, is analogous to the linear Faraday instability problem. Unforced nonlinear simple pendulum. No, but the unforced nonlinear case, we again we have already solved that problem. We do not get any Matthew kind of equation. So option C, copies the pendulum is analogous to the linear Faraday instability problem. That is true. When we tried to solve the stability analysis of the Kapitza pendulum, we derived the Matthew equation. So it is analogous to the linear Faraday instability problem. Option D, oscillation in unforced surface gravity waves is analogous to the Faraday instability problem. No, obviously. Question 4. What is the condition of the interface at bed state in case of Faraday instability? Interface is flat and it is moving up and down because of the forcing. In the oscillation frame of reference, the moving interface appears stationary. Obviously. So this is your container, this is your fluid, and if you are just oscillating it, it will go up and down. Now if you are standing on this, if you are sitting on this interface on this reference frame, you will just see that nothing is happening. So option A is correct. Interface is wavy. Option B, interface is wavy and not moving up and down. Wrong. Oscillatory interface wrong. Interface atomization creates droplets. No, wrong. Okay. Consider the following stability chart for the Matthew equation of this kind and select the correct option. Okay. So there are 3 points. One inside the subharmonic term, one in the stable region, and one inside the harmonic term. So this is 1, this is 4, right? Oh, okay. The question is asterisk sky blue, that means this symbol is unstable and pi periodic. Is it pi periodic? So what is the case basically? So in this case, your omega is equal to your omega by 2. Okay. So here the solution is 2b cos t. So here your period is 2 pi. That means for when omega equal to omega by 2. Okay. So just a second. It is cos t. So t equal to t plus 2 pi cos t. Right. So now cos omega t. So to cos. So in the non-dimensional sense, it will be the response will be when your forcing frequency is of t, your cos t, it will the response will be cos t by 2 inside the subharmonic regime. Okay, so your time period will be 4 pi. Okay, so obviously this option A is not correct. Second option, asterisk sky blue, unstable and 2 pi periodic. No, it has to be 4 pi periodic. But let us look at the other option, brown plus unstable and aperiodic. No, it is a stable region. Sorry, I should. Okay. Diamond deep blue, unstable and 2 pi periodic. Yeah, this is 2 pi periodic because here also the response will be cos t. So t plus 2 cos t plus 2 pi will be cos t. Option C. Asterisk sky blue, unstable and 4 pi periodic. Yeah, this is the correct. Option B, brown plus stable. True, this is the stable. And diamond deep blue, unstable and 2 pi periodic. This is correct. So option C is the correct option. Let's see at D. Asterisk sky blue, unstable and pi periodic. So this is also incorrect. So answer C is the correct. Is the only correct option. Okay. 6. Select the correct statements. So there are more than one answer. About a Matthew equation of this kind. In Matthew equation, A is the ratio of natural frequency and forcing frequency. True. If B equal to 0, Matthew equation, in the Matthew equation, you solve it using normal mode analysis. True. A stands for strength of forcing. No. Floquet analysis is the generalized form of the normal mode analysis. It is also true. We have discussed that during the discussion of what happens the method. Okay. Alright. Now question 7. One important consequence of Faraday instability droplet atomization. Droplet atomization will occur when forcing amplitude is large enough for a given forcing frequency. Now, why? That if you go deep, okay, your linear solution will say that it will just exponentially grow in time, but that doesn't happen. Okay, but you can understand. Suppose you have a cylinder like this. Now, if you're forcing like it, you will get now a shape like this. So you have a Bessel function. Bessel function, I have also already shown the shape. The shape of the Bessel function is something like this. Now it will go high. Okay. Now here, there, because of the Rayleigh plateau instability, it will break into small droplets. Okay. So you will frequent for very high acceleration or the forcing, you will get droplet automation. So in the extra class, I will show some video about this. Okay. So okay. So now okay. So that's all. So now I one more question. Okay. This is related to the Rayleigh plateau instability. So you have in the Rayleigh plateau instability, we have a shape like this. We know that when kr is less than 1, it is unstable. Now I am giving forcing in the radial direction. Okay, in the radial direction, I am giving the forcing of this kind, so it will do something like this. Okay, and I have already also provided some perturbation. Okay, we have derived this for the unforced case. Now the forcing has a particular form. Let me give you the form of the forcing. Just a minute. Forcing is if RT is equal to minus H R by R naught cos omega T. This forcing is dependent on the instantaneous radius of the cylinder of the jet. Okay, R naught is the j radius at the base state. Okay, and omega is the forcing, and h is the forcing strength. Now you are told to calculate the base pressure at the base state. Okay, so now I have already told you there and show what will be the relation. Okay, so don't think it like that. Yeah, you can think it like that. So what is the term? Just a moment. Yeah. So you have the expression grad p equal to g. Okay. So let me work with that. It is g r minus g e z minus. Let us. So grad p is equal to g p. So it will be. So in the so we are only interested in the, yeah, radial direction. So gt is this term. So 1 by rho. Then in the base state, it will be only del pb del r is equal to minus h r by r naught cos omega t. Okay. So now let us integrate it. So del pb del r. So this is only function, pb is only function of r, right? So dpb dr is equal to minus h by rho cos omega t r by r naught. It will be h into rho. Okay. So dpb is equal to minus h rho by r naught cos omega t integration r dr. Now it will vary from the base state radius to some arbitrary radius. Okay. So if you do that, we will get rho h. This is PB by 2 r naught omega t r naught square minus r square. But wait, there is one correction. Now see, What will be? So let us not solve it in this way. RDR, okay, plus some constant C. So it will be minus 0 by R naught cos omega t r square C. Now what will be the pressure at the base state when t equal to 0? No, this is PVR. Okay. Now what is PV R naught? R equal to R naught. So it will be minus H rho by 2 R naught cos omega t R naught square plus T by R naught. So this term will add in the equation, because at the base state you know that there will be one T by R naught term by default because the interface is curved. So your final PV of R will be rho H by 2 R naught square minus R square cos omega t plus T by. Okay. All right. So that's all for today, and I will meet with you in the next.